Advances in global engineering in the development of highly efficient and economical gas turbines by the 1950s allowed machine builders to attempt to use various gas turbine engine designs in automobiles and tractors. The most suitable option for using a gas turbine as a propulsion engine in such vehicles at the time was seen as a hybrid piston turbine engine, which combined two separate units, a piston gas generator and a gas turbine propulsion unit. In 1957, Ford Motor Company published data on the experimental Ford Typhoon tractor. Its power plant consisted of a gas generator based on a diesel free-piston engine, and torque for the drive wheels was generated by an axial gas turbine. This film will discuss the design of the Ford Typhoon tractor and some of the experimental results. Gas turbine engines of any configuration consist of three main components: an air compressor, a fuel combustion chamber, and a gas turbine. The combined turbo-piston engine has a unique feature. The compressor and combustion chamber are combined into a single unit, a piston gas generator, separated from the turbine and connected to it by a gas pipeline. Most often, a two-stroke free-pistons diesel engine is used as the gas generator for such hybrid engines. This power plant, in general, can also be called a free-piston turbine engine. Due to the broad scope of the term free piston, many engine configurations fall into this category. However, the term free piston is most often used to refer to a linear engine that lacks a crank mechanism. The piston is free because, unlike conventional engines, its motion is not controlled by a crankshaft, but determined by the interaction of forces from the combustion chamber gases, a rebound device, and a load device. Since free-piston engines lack a crank mechanism, power is not delivered to the crankshaft to generate torque, but creates a linear load along the piston stroke. This force can be used to drive machines that perform reciprocating motion. The free-piston engine is usually restricted to the two-stroke operating principle, since a power stroke is required every fore and aft cycle. However, four-stroke versions have also been patented. There are several configurations of free-piston engines depending on the number of combustion cylinders. They can be single-piston, twin-piston, or with opposed pistons and a common combustion chamber. A classic free-piston engine consists of a cylinder with two counter-moving pistons and a uniflow scavenging port located inside a housing that serves as a scavenging receiver. Compressors are mounted at the ends of the receiver, their pistons rigidly connected to the engine pistons. Between the outer covers of the compressor cylinders and its pistons are enclosed cavities that act as pneumatic bumpers. To start any diesel engine, the air in its cylinder must first be compressed. In this type of engine, it is obviously necessary for both pistons to move toward each other, toward the center of the cylinder. This is accomplished by using compressed air from a special external receiver supplied through starting valves to the outer air chambers of the compressor cylinders. The starting air forces the pistons to move and compress the air, first in the inner compressor chambers, and then, when the pistons close the scavenging ports, in the compressed air chamber. At the end of the compression stroke, the air in the compression chamber accumulates and compresses, preparing to scavenge the combustion chamber. The air in the diesel cylinder continues to compress, increasing pressure and temperature. When the air temperature exceeds the auto-ignition temperature of the fuel, it is injected into the cylinder through the injector. The fuel ignites and burns, causing the cylinder pressure to rise sharply to 100 to 130 bar. The engine's power stroke begins, during which the combustion products expand and push the pistons in opposite directions. The suction valves in the internal compressor cavities open, allowing atmospheric air to rush in. In the rebound devices, air is compressed, creating air cushions. As soon as the engine pistons open the scavenging ports, compressed air from the compressed air chamber rushes into the cylinder, performing the scavenging action. The pistons stop when the pressure in the air cushions reaches a level sufficient to prevent their further movement. Then, under the influence of the air cushion, the pistons begin to move in the opposite direction, and the cycle repeats. Although a number of inventors worked on the free-piston engine, the primary credit for its development goes to Raul Pateras Pacara, an Argentine-born inventor and helicopter pioneer who lived and worked in Europe, primarily in France. He began building free-piston engines in 1922, believing they could power the helicopter he had designed. The first of these were spark ignition engines, and later, diesel engines. Pacara patented his designs in 1932. Free-piston engines were not suitable for helicopters, but their potential for use in other machines, primarily as compressors, showed promise. In particular, the German company Uenkers began developing similar air compressors, which were used to supply compressed air to torpedo launch tubes on German submarines during World War II. Another way to extract power from a free-piston engine was to use the pressure of its exhaust gases to rotate a turbine. In this combination, it was no longer a drive motor, but a power generator, part of a combined turbo-piston engine. A free-piston gas generator was also called a crankless gas generator. Internal combustion engines have become widespread due to their relatively high efficiency and a number of other advantages over other engine types. However, they also have some disadvantages, one of which is that they do not fully expand an ignited air-fuel mixture. This is clearly evident in the fact that the engine exhaust gases are released into the atmosphere while still under pressure, retaining some energy. A simplified indicator diagram of the compression and expansion strokes of an internal combustion engine will explain the essence of what is happening. As we know, an indicator diagram records how the gas pressure in the engine cylinder changes at different stages of the piston stroke, that is, as the cylinder volume changes. The vertical y-axis of this chart represents the cylinder pressure, and the horizontal x-axis represents its volume. From point 4, the air-fuel mixture the cylinder is compressed, and at point 1, when the piston approaches its maximum upper position, the mixture is ignited by a spark plug for petrol engines or by self-ignition for diesel engines. Further, up to point 2, the mixture burns intensely, accompanied by a sharp increase in gas pressure while the volume remains virtually unchanged. From point 2 to point 3, the ignited air-fuel mixture expands and pushes the piston downwards. In this section, expansion work occurs, that is, the piston's power stroke. The expansion of the gases continues until point 3, where the exhaust valve opens and exhaust gases begin to exit the cylinder. At this point, the pressure in the cylinder drops to atmospheric pressure. Next, the cylinder is purged and filled with the fuel mixture for the next cycle. But let's return to point 3. As you can see, the moment the exhaust valve opens occurs well above atmospheric pressure. The gases have not yet fully expanded and still contain some energy at the moment they must escape while still under pressure. Is it possible to convert this residual energy of the gases into useful work rather than lose it? Theoretically, this is possible. The gases should expand completely in the cylinder, and the exhaust valve should open not at point 3, but at point 6, when their pressure drops to ambient pressure. However, in practice, this is difficult to achieve, as it would require increasing the combustion chamber volume to the same point 6, resulting in a very large cylinder volume. This would increase the engine's size and weight, and also increase heat loss through the cylinder body. Therefore, engineers design cylinders with limited volume, thereby accepting the inevitable energy losses. Energy losses from incomplete gas expansion in internal combustion engines are quite significant, reaching approximately 25%. On an indicator diagram, the work not performed due to these losses can be shown by shading the area of the imaginary additional expansion. In turn, the area bounded by the lines of the actual diagram characterizes the useful work performed by the gases during the engine's working cycle. The energy from the engine's exhaust gases is sometimes harnessed to perform additional work. For example, using an ejector, the exhaust energy can be used to suck dust from the engine's air filter or to provide engine cooling. An ejector can also be used to draw liquid into tractor-trailer tanks and then discharge it, also using the exhaust gas. This same principle was used in automatic refueling systems for tractors and is used in pneumatic seeders. Some tractors and combines used exhaust-powered horns. Another way to utilize exhaust energy is with a gas turbine. A simplified indicator diagram of a gas turbine looks like this. The gases fill the turbine to point 5, then expand along line 5 to 6, acting on the rotor blades and thereby rotating the rotor. As can be seen, unlike piston engines, a gas turbine completely expands the gas. At the end of the expansion, their pressure exceeds atmospheric pressure only by the amount of exhaust pipe resistance. Therefore, if a turbine is connected to the exhaust system of an internal combustion engine, it will completely expand the gases, and the residual energy in the exhaust gases will perform work. This work will, of course, be significantly less than that of the main engine, but if it is used in parallel, as is done for example in a turbo-compound engine, or even to drive some auxiliary mechanisms, such a system will be more economical than a single engine. However, these are very complex design options, requiring the use of complex transmissions. It would be simpler and more efficient if the turbine transferred its power to an air compressor, which would then force air into the engine cylinder. In other words, turbocharging the engine. The benefits of turbocharging are well known. Increased engine power, reduced engine weight relative to its power output, reduced fuel consumption, and more. The turbine's work in this case will be approximately equal to the compressors, since they are located on the same shaft. The turbine works entirely for the compressor. The turbine remains a low-power auxiliary device, while the engine performs the main work. But why not consider increasing the turbine's output so that it performs main work instead of the engine? In some vehicles, a turbine offers certain advantages over a diesel engine, particularly a huge torque reserve. However, using a gas turbine engine in its traditional design for such applications has encountered difficulties. The gas turbine's ability to fully expand the working gases has already been noted. However, the turbine also has a significant drawback. It is impossible to significantly increase the gas temperature before its blades. But it is known that the higher the temperature and pressure of the gases before expansion, the more work they will perform in an expansion machine of any type. Due to the limited working gas temperature in a gas turbine, its efficiency is lower than that of a diesel engine, which develops very high pressures at high temperatures, approximately 2,900 degrees Fahrenheit. Moreover, in a diesel engine, as has already been noted, the working gases are not fully expanded. While considering the pros and cons of the two engine types, engineers came up with the idea of combining them to complement each other. Calculations showed that by increasing the engine intake air boost pressure to 5 to 6 bar, the power of the compressor and turbine would be approximately equal to the power developed by the engine. Thus, the roles of the engine and turbine could be reversed. By decoupling the compressor and turbine, it would be possible to achieve a situation where the engine drives the compressor, while the turbine would serve as the power source for the payload. This resulted in a combined gas turbine unit with a piston gas generator, combining the positive qualities of an internal combustion engine and a gas turbine. High temperatures, unsuitable for a gas turbine, were handled by the diesel engine, and its power was expended on the compressor. The low-pressure, high-volume region was handled by the gas turbine, which had advantages over the diesel engine in this regard. Another question: is it necessary in this case to use a conventional internal combustion engine, with its crankshaft, connecting rods, camshaft, multiple bearings, and so on, to generate gases? After all, this task could be successfully accomplished with a simpler gas generator based on a free-piston engine, which combines both the combustion chamber and compressor. Although examples of crankshaft-based gas generators exist in mechanical engineering worldwide, free-piston gas generators are more common. By and large, by creating a combined turbo-piston engine, the designers haven't made any breakthrough in engine engineering. They haven't invented anything new. They've simply repurposed existing systems with specific capabilities, which has yielded certain advantages. The first combined gas turbine engines with free-piston gas generators demonstrated a number of advantages over constant pressure combustion gas turbines and conventional diesel engines, which were used at the time in the power generation and large transportation. It was claimed that the fuel economy of such units was on par with traditional diesel engines and 80 to 90% better than that of conventional gas turbines. For example, a 1,000 horsepower turbo-piston engine consumed about 0.39 pounds of fuel per horsepower hour, compared to 0.37 pounds for a large diesel engine and about 0.64 pounds for a conventional gas turbine. The overall efficiency of some high-power engines reached 35%. This was comparable to, or even better than, diesel engines and other engine types. The free-piston engine has a number of unique features. Some give it potential advantages, and some represent challenges that needed to be overcome. Since the piston's movement between endpoints is not mechanically constrained by a crank mechanism, the free-piston engine has the valuable property of variable compression ratio. This variable compression ratio allowed the use of different fuels with different auto-ignition temperatures. It performed well on high-octane gasoline, diesel fuel, kerosene, shale oil, butane, and even peanut and other vegetable oils. Free-piston engines were completely balanced machines, virtually free of vibration, allowing them to be installed without the need for massive foundations. A common trick used during demonstrations was to place a pencil or coin vertically on the horizontal surface of a running engine, and they wouldn't fall. The simplicity of the design and the relative lightness of the components significantly simplified the manufacture, maintenance, and repair of these machines. Their cost was almost half that of diesel engines of the same power. The traction turbine was significantly smaller than in conventional gas turbine engines of equivalent power, since all of its power was efficient. In a conventional gas turbine engine, the compressor is typically mounted on the same shaft as the turbine. So the turbine transfers its power not only to the payload but also to drive the compressor. This power transfer is quite significant, approximately 70%. If the turbine has a capacity of 1,000 horsepower, only 300 of this goes to the driven unit and 700 to the compressor itself. In a free-piston gas turbine unit, the compressor and turbine are two separate units, so the turbine's power is used only to drive the payload, and its size can be significantly reduced. Another important point, because a large amount of scavenging air was injected into the gas generator cylinder during scavenging, its exhaust temperature was slightly lower, and the gas temperature before the turbine was relatively low, approximately 1,100 degrees Fahrenheit, as opposed to the 1,650 degrees Fahrenheit found in conventional gas turbine engines. This allowed for a simpler turbine design, using inexpensive heat-resistant steels rather than specialized alloys. This reduced cost and increased reliability and durability. Free-piston engines also had significant drawbacks. The main problem with a free-piston engine is its control. Although the pistons are free to move, this movement is not arbitrary. They must remain within certain limits, which determines the engine's operating mode. To ensure that both pistons operate synchronously and reach their extreme positions simultaneously, they are linked by a special rack and pinion synchronizing mechanism. Although a crankless engine can operate without this, its pistons will move freely under the action of gas pressure and air buffer, but in this case, even a small deviation in the synchronous speed of one of the pistons can disrupt the working process of the machine. A number of factors influence the piston stroke length and the piston cycle rate, which alters the compression ratio and, ultimately, the engine's power. Therefore, active control of the piston stroke during engine operation is necessary. This is accomplished primarily by regulating the fuel supply. Piston stroke also depends on the air pressure in the return buffers. The piston cycle rate of a free-piston engine depends on the weight of the pistons. The lighter they are, the faster the engine can run. Two engines with the same dimensions, but with cast iron pistons in one and aluminum pistons in the other, will have different piston cycle rates and, consequently, different power output. Adding to the difficulties is the absence of rotating parts in a crankless engine, which creates significant challenges in driving the fuel and oil pumps, the coolant pump, and other auxiliary components. Developing a piston oil capable of operating at high temperatures has long been a challenging task. This issue was one of the most challenging. Other issues also arose, which will be discussed below. The attractive economics and design advantages of free-piston gas generators led many companies in the 1940s and 1950s to turn to this technology and build units that were successfully used in marine and industrial power plants and, with limited success, in large-scale transport. In 1945, the French company Sigma, using Pokhara patents, built the Sigma GS-34 free-piston gas generator with a capacity of over 1,000 horsepower, 745.7 kilowatts, for powering gas turbines and stationary power plants. This was the most successful free-piston gas generator in history. 90 of these, with a total of approximately 250,000 operating hours, were in commercial service in 1957. The largest user was the Cherbourg power station, where 8 gas generators powered a single 6,000 kilowatts turbine. In 1952, the French Renault built a free-piston gas turbine locomotive with a 1,000 horsepower output and an overall efficiency of up to 33%. Notably, this gas turbine locomotive used mechanical power transmission to the wheels. Its efficiency was significantly higher than that of an electric transmission. The Renault locomotive required an auxiliary 90 horsepower diesel engine to drive various auxiliary equipment. A similar locomotive with a capacity of 1,300 horsepower was built by the Swedish company Götaverken. 21 French Sirius-class minesweepers, built since 1952, with free-piston gas turbine propulsion systems, remained in service for 15 years or more and received favorable reviews. However, a marine propulsion system based on 6 free-piston gas turbine units with a total output of 6,000 horsepower, installed on the American transport vessel SS William Patterson in the late 1950s, demonstrated disappointing results. Based on the operational experience of the William Patterson, the U.S. Navy abandoned the free-piston concept. In 1956, General Motors experimented with the GM XP 500 Firebird passenger car, equipped with a twin-piston gas generator producing 250 horsepower, a 5-stage axial flow turbine, and a 7:1 reduction gearbox. This car's power plant could run on virtually any fuel, including kerosene, fuel oil, and vegetable oil. It was reported to be virtually vibration-free, with thermal efficiency ranging from 32 to 36%. However, problems with starting, lubrication, and engine control apparently proved insurmountable, and the experiment was abandoned after 3 years. The Firebird remained a prototype. Why did tractor manufacturers become interested in this type of engine? Theoretical calculations suggested that combining a piston gas generator with a turbine would create a tractor engine with very efficient fuel consumption, approximately 0.25 pounds per horsepower hour. This was better than any other automobile or tractor engine at the time. Among the other advantages of the free-piston engine, the designers were attracted by its very high torque flexibility or engine flexibility coefficient. This was important for a tractor. This torque reserve helps the tractor overcome sudden, short-term overloads during operation without stopping or shifting gears. The traction curve graph shows that with increased load and the resulting reduction in engine speed, the towing capacity of a piston tractor decreases, while that of a gas turbine tractor increases. This is because tractors with conventional diesel engines had a torque reserve of 12 to 15%, while gas turbo engines had a torque reserve of 250 to 300%. The absence of a rigid mechanical connection between the gas generator and the gas turbine ensured smooth torque changes. This reduced wheel or track slippage, which should have increased the tractor's productivity. Due to the absence of a crankshaft, connecting rods, shaft bearings, flywheel, cylinder head, valves, rocker arms, and camshaft, the crankless engine had fewer parts and fewer friction pairs than conventional piston engines. This should have increased its mechanical efficiency and wear resistance. Furthermore, due to its complete balance and the absence of harmful vibration, this engine could be installed on a simpler frame. Since the gas generator and turbine were independent units, their installation on a tractor was very convenient. The gas generator could be installed under the hood, and the turbine somewhere in the transmission, connected by a gas line. Since the piston speed during engine startup was close to nominal, the compression ratio at this point reached 50:1, eliminating the need for preheaters at low ambient temperatures. High compression temperatures and pressures, as well as excellent starting characteristics, ensured reliable operation of the tractor's turbo-piston engine on any liquid fuel, from 100-octane gasoline to high-sulfur fuel oil. Ford worked on a combined turbo-piston engine for tractors for several years, and the result was the free-piston gas generator Ford 519, which along with a traction turbine was installed in the experimental Ford Typhoon agricultural tractor in 1957. The Ford 519 Packard gas generator provided the engine with 50 horsepower at 2,400 cycles per minute. By replacing some components, the unit's output could be increased to 100 horsepower. The diesel cylinder diameter was 3.75 inches, and the compressor cylinder diameter was 11 inches. The piston stroke varied from 4.2 inches to 6.8 inches at different operating conditions. The compression ratio in the diesel cylinder at the calculated power was approximately 30:1. The gas pressure at the generator outlet was about 3.62 bar. The second part of the engine, the radial traction turbine, was quite compact, with a 5.5-inch impeller diameter and a rotational speed of 43,000 revolutions per minute. The turbine was mounted in a single unit with a two-stage mechanical gearbox, with an overall gear ratio of 21.5. Thus, the transmission input shaft rotated at 2,000 revolutions per minute. After the gearbox, torque was transmitted to a conventional manual transmission, providing 10 forward gears and 2 reverse. The Typhoon tractor's power unit, assembled, weighed 1,115.5 pounds, almost 3 times less than a diesel engine of similar power. Feed air to the gas generator entered through a front-mounted air intake and filter. Gas was supplied to the turbine through a gas pipeline. Unfortunately, tests of the Typhoon tractor revealed that its turbo-piston engine performed worse than expected based on calculations. Actual fuel efficiency was significantly lower, and a number of issues were identified that hindered achieving the desired results. It turned out that small-sized free-piston gas turbine units had significantly lower efficiency than similar high-power units. This was explained by the fact that small-sized units were faster. Attempts to improve performance by increasing boost were unsuccessful. This increased the heating of the gas generator's cylinder piston assembly. Overheating also increased heat loss. The gas generator suffered from insufficient stability due to changes in piston stroke length at different operating modes. This was especially noticeable at partial loads, where misfires occurred. Misfires in such an engine were a significant problem, as it lacked an energy storage device, such as a flywheel in a conventional diesel engine. A number of other problems were also reported. When Ford executives asked their engineers, after several years of work on the free-piston gas turbine unit for the Typhoon, whether mass production of this tractor was feasible, assuming full funding and orders, they replied that they would prefer to work on the engine for some time. But that time was no longer available. Extensive efforts to improve conventional diesel engines were yielding results, and their efficiency was continually improving. The introduction of turbocharging on diesel engines with a power of about 300 horsepower made it possible to achieve a specific fuel consumption of up to 0.37 pounds per horsepower hour, while the combined turbo-piston engine of the Ford Typhoon tractor with an overall efficiency of about 35% demonstrated a specific fuel consumption of about 0.55 pounds per horsepower hour. As a result, the free-piston gas turbine engine never became a real competitor to either the diesel engine or the conventional gas turbine. In the early 1960s, further development of this technology for small vehicles was practically abandoned. The main reason for this failure was the difficulty of controlling the piston stroke, which was never fully resolved. This led to a chain of other problems. Only in subsequent decades, with the development of microprocessor technology and the emerging possibility of creating reliable and high-speed piston stroke control systems based on it, did interest in the free piston engine somewhat renew.